Today, I'd like to talk to you about the relativistic Doppler effect and Hubble's law. But first, I'd like to review the classical Doppler effect so that you can kind of remember what the Doppler effect really is. So the classical Doppler effect is the observed change in frequency or wavelength of sound that occurs because of the relative motion of the source or observer of a wave. So when the source and observer are moving towards one another, the frequency appears to increase. And when the source and observer are moving away from each other, the frequency appears to decrease. Now, you might remember or have recognized what this means if you stand on the side of the road and you listen to the sound that the cars make as they go past you. So as they're approaching you, they have a higher sound, and as they move away from you, they have a lower pitch sound. So it goes like this, right? And you might have also heard this in police cars and sirens, that they get a lower pitch as they move further away. Now this is all due to the fact that sound waves need a medium to propagate. So you might have heard that the speed of sound in air is something like 340 meters per second, depending upon the temperature. And as the temperature of the air changes, or if it moves through a medium other than air, the speed of sound will also change. So you could see from the properties of the medium, since that dictates the speed of the sound, that obviously a medium is necessary for sound, right? There's no sound in space, despite what you might have seen in the Star Wars movies when the TIE fighters go by, right? Totally incorrect physics there, by the way. So the medium of the wave, in this case sound, dictates its speed and a lot of the other properties like the observed frequency. If something is moving, therefore, relative to that medium, then the medium becomes the preferred reference frame for the sound, if that makes sense. And that's why we get our classical Doppler effect. Now, just to remind you, the equation for the classical Doppler effect that you might have seen in an introductory physics class is given here. Now, either the observer or the source can be moving to cause the change in the observed pitch of the sound, and then you compare their speeds to the speed of sound in your medium. We'll call the speed of sound in the medium V, the motion of the observer of the sound V sub O, and the motion of the source of the sound V sub S. Okay? So then you have F prime, which is the observed frequency, is equal to V plus V0 divided by V minus Vs times the frequency at the source. Now the sign for these things, for the velocities in that equation, depends upon the direction of the velocity. A positive value is used for motion of the observer or the source towards one another, and a negative sign is used for motion of one away from the other. And so you can see why the frequency shifts the way it does when the police car drives by and the siren's on. Now the relativistic Doppler effect is a little different. The classical Doppler effect is the result of the motion of the emitters and the receivers of the wave with respect to the medium. But as we've already discussed in this series of lectures on special relativity, light has no luminiferous ether, okay? So light does not need a medium to propagate. It can propagate in the vacuum of space. So that means that the cause of the relativistic Doppler effect has to be from a different source, and it is. The relativistic Doppler effect is the result of the constancy of the speed of light in all reference frames, combined with the equations for time dilation. As you might remember, frequency is, in terms of units, just an inverse time. So you could see that if something with the time shifts, then obviously something with the frequency has to shift too. And when that happens, remember you've got c is equal to lambda f, and so the observed wavelength will change as well, since the constancy of the speed of light is 3 times 10 to the 8th meters per second in all reference frames, right? That's the upper limit for the vacuum value. And if you change your frequency, you have to change your wavelength too. Now, your book, Crane's Modern Physics, does a nice derivation for the source and receiver receding from one another. Be sure to check that out and read that text. So this is the root cause of the Doppler effect, as I said. I'm going to do the opposite derivation in class, but I'm not going to do it in this online video. Derivations are a little cumbersome in videos. People have a tendency to tune out, okay? Now, in the equations for the relativistic Doppler effect, what we're going to say is that the frequency of the source is measured within its own reference frame, okay? So it's the source frequency is from the emitter of the light. And the shift depends upon the relative velocity of the source and observer. So if the frequency observed is greater than the frequency at the source, that's a blue shift. and that's when the source and observer approach each other. If the observed frequency is less than the frequency at the source, that's when the source and observer are moving away from each other, and this is known as a redshift. Now, in terms of which direction the shift goes and whether they're receding from or approaching one another, this is the same kind of relationship that we saw in the classical Doppler effect. So things are kind of as expected. If they're moving away, the frequency is less. If they're moving towards, the frequency is greater. Kind of the same idea. Now, just to put it in perspective, the reason they're called red shifts and blue shifts is because of our visible light spectrum here. Okay? So the red corresponds to a wavelength of about 700 nanometers, and the blue or violet end of the spectrum is at 400 nanometers. Now remember, C is equal to lambda f, so shifting to longer wavelengths means shifting to lower frequencies because they're inversely proportional to one another, okay? And vice versa. So here's the equation for the relativistic Doppler effect. We can put it into one equation if we agree to the convention that, first of all, beta, or the little shorthand that I sometimes like to use for the ratio of the speeds, beta is equal to u over c. If we put a plus sign on that beta when the source and receiver are approaching one another, and we put a minus sign on that beta when they're receding from one another. And in the remainder of this lecture, I'll do an example of each. Okay, so hopefully it'll be pretty clear what I mean there. So here's the first example, and it's a classical example, or I guess I should say the canonical example for the Doppler effect. I've seen it in every modern physics class I've ever done, so here you go. An astronaut is said to have tried to get out of a traffic violation for running a red light, red here is 650 nanometers, by telling the judge the light appeared green, 540 nanometers, to her as she passed by in her high-powered transport. If this is true, how fast was that astronaut going? Okay, so like I said, you've seen it. I've even seen it in bumper stickers. You might have seen, if this sticker is blue, you're moving too fast, I think. So that's pretty funny. But anyway, here's how you would solve that. We're going to use that equation that I gave you for the relativistic Doppler effect. F is equal to F naught times the square root of 1 plus beta over 1 minus beta. Now, F naught is the frequency at the source, and F is the frequency that's observed. Okay? So here, beta is what we're solving for. Now, we do know that she's going to be approaching the light, and so what that means is that in this case we're going to use beta is equal to plus u over c. Remember, that was a convention. If you use the plus u over c, if the source and receiver are approaching one another. So I've just left it here, 1 plus beta, 1 minus beta, and we're good to go there. Now remember, c is equal to lambda f, and so I'm plugging in for the source frequency and weight, or for the source wavelengths here by taking that ratio. So the observed is, remember, green, so that's C over 540 nanometers, is equal to the frequency at the source, which would be C over 650 nanometers, and now times that square root of 1 plus beta over 1 minus beta. Now, to a physicist, I guess this is sort of basically a solved thing. You just have to go through algebra to figure out what beta is, which will give you your speed. And so following through on some of that algebra, I'm just going to move my wavelength over to the other side of the equation. So I multiply both sides by 650 nanometers. I can cancel out my speed of light since that appears on both sides of my equation. And then I get the ratio of 650 nanometers divided by 540 nanometers. Now, since I'm dividing a wavelength by a wavelength, the units are the same. They cancel out, it's dimensionless, which is good since beta is a dimensionless number as well. Then to get rid of that square root, I have to square both sides. And so I end up with 650 divided by 540 squared is equal to 1 plus beta over 1 minus beta. Now, I multiply both sides of my equation by 1 minus beta to get that off the denominator. And then I'm going to rearrange my equation and group terms for beta on my right-hand side, and then group the terms that don't contain beta on my left-hand side. When I do that, I get 650 divided by 540 squared minus 1 is equal to beta times 1 plus 650 divided by 540 squared. All right? Then I just divide both sides by that 1 plus 650 over 540 squared factor to get beta isolated on one side of my equation, and I solve. And so I end up with beta is equal to 1.45 minus 1 divided by 1.45 plus 1, and that's equal to 0.18, okay? Which means basically that the astronaut would have to be going 18% of the speed of light in order for that observation to be true. So when you multiply through and then do the conversion to convert that into miles per hour, the astronaut was going 123 million miles per hour. And I'm pretty sure that that breaks any posted speed limit that we have here in the United States. So I'm pretty sure that they were still breaking the law. Okay. Now, one really fun application of this relativistic Doppler effect has to do with measuring the distances to stars. So let me back up a little bit. In 1885, J.J. Balmer, pictured over here, studied the visible part of the hydrogen spectrum. Basically what this means is that if you excite a hydrogen gas, a hydrogen atom, then the light emitted from that excited gas will always have the same spectrum to it, okay? And to do that, you can just pass the light from the excited gas through a prism, and that'll spread out the colors. And instead of a rainbow, which you would see for white light, you see this series of single lines, okay? And they always occur at the same wavelengths, these lines, and they have very distinct colors like that. So the evidence for that, documented by Balmer and then later other parts of the spectrum, the infrared, the UV, so on and so forth, were documented by other physicists and astronomers. Then what happened was astronomers noticed that when they passed the light from distant stars through these prisms, then they saw the same spectra, the same spacing in the spectra as that characteristic hydrogen spectrum, and this led us, among other evidence, to believe that hydrogen is present in stars and is used actually as the fuel for the stars. So this is one of the ways that we know that stars contain hydrogen, because we see this characteristic light spectrum. However, astronomers did notice that although the spectrum was there, and it's kind of like a little fingerprint, the actual raw values for those wavelengths weren't quite the same when they came from more distant stars. And then this happened a little later. They noticed that the hydrogen light spectrum from many stars was actually redshifted. Now, Edwin Hubble, he related the distance of the star from Earth to the degree of the redshift. And this became known as Hubble's law. Hubble's pictured here, and this is his paper, which was published in 1929, a little screenshot of his paper. So here's Hubble's law. D is equal to U over H. Now here D is the measured distance of the star from our planet, and U is what we call the recession speed, which is the speed that Hubble calculated based upon the degree of the redshift. And then this H is a constant that has become known as Hubble's constant. And the value of that constant is 2.32 times 10 to the minus 18 inverse seconds. I should note that Hubble's constant is one of those fundamental constants that we know to a smaller degree of precision than many others. Now, Hubble's results led all astronomers to conclude that stars that are far away from us are actually moving away from us. And in fact, all stars that we see that are distant from us are moving away from us, which was an interesting conclusion. And then he also understood from that the further a star is away from us, the faster they're moving away from us, which we'll talk about a lot in modern physics too when we cover cosmology. But suffice it to say for now that Hubble's results led to the development of what became known as the Big Bang theory, basically showing that all stars and planets are moving away from each other and postulating that this started at the beginning of the universe when the expansion began. So we can use Hubble's law now to get an estimate for the distance of an astronomical object from us. And here's an example problem for that. Yellow light at 587.6 nanometers, which is characteristic of the helium spectrum, is found to be redshifted as it's observed in the spectrum of a certain star. The measured wavelength from the spectrum of the star for that line is 611.7 nanometers. So from this, how fast is the star receding from Earth, and then use Hubble's law to estimate the distance from Earth. So here we go. Here's our equation for the Doppler effect. F is equal to F naught times the square root of 1 plus beta over 1 minus beta. Now remember that we said that if things were moving towards one another, then beta was plus u over c, and if things were moving away from one another, it was minus u over c. So whenever it's a Hubble's law type problem, you're going to have the minus u over c. And that's what I've plugged in here in the top line. 1 plus beta becomes 1 minus u over c. And you can really just sort of think of that as a vector quantity, if you'd like, in 1D with the plus or minus sign indicating the direction of your velocity vector. Now I also plugged in for the frequency, which I just put in as a wavelength again, c over 611.7 nanometers, because c is equal to lambda f. And then here's the frequency at the source, c divided by 587.6 nanometers. So just like last time, I canceled out my speeds of light, and then I multiplied both sides by the wavelength here on the bottom, and I get 587.6 divided by 611.7, and I square both sides to get rid of that square root. Then I multiply both sides by the denominator here on the right-hand side, 1 plus u over c, and I end up with that. And then, yet again, I group like terms. I take all the factors that multiply u over c and move them to the right-hand side of the equation, and then take everything that doesn't have u over c and put it on the left. Just a little bit of algebraic manipulation, but please do feel free to pause the video and make certain that you can follow the steps that I've laid out here. Then all it takes here is to solve for u over c, and I did that here in this ratio, 1 minus 587.6 divided by 611.7 squared over that same ratio squared plus 1, and it turns out that 587.6 divided by 611.7 squared is 0.923, so then I plugged that in there. So I end up with 1 minus 0.923 divided by 1 plus 0.923. And that ratio gives me 0.04, which means that the star is receding from us at 4% of the speed of light. Now, u is equal to 0.04c, which is 1.2 times 10 to the 7th meters per second, just to check your multiplication skills there. And now I plug that speed, remembering to use my SI units here, the meters per second, into my Hubble's law equation. And then I end up with 1.2 times 10 to the 7th meters per second divided by Hubble's constant, 2.32 times 10 to the minus 18 inverse seconds. When I do that, I get a distance to the star of 5.2 times 10 to the 24th meters. Now that's a big number, but let's put it in context. If you convert that number to light years, which I think more people understand is a really big number, right? Then you end up with about 550 million light years. So that star is 550 million light years distant from us. I think we can all agree that's a pretty epic distance in terms of our everyday experience. All right, so that sums up sort of a brief introduction to the relativistic Doppler effect. As always, be sure to read your book, and I'll see you next time. Please let me know if you have any questions.